So last time and all so far, yeah, again, sorry for the technical issues. So we said that there is a state function entropy which depends on NVE. This was our starting point. And from this, we have been able to transform things in different way. We said due to the monotonicity condition, we can also think about E of NSV. And this is also going to be a fundamental relation. It is thermodynamically complete. Then we introduced other state functions. We introduced H, because we showed that delta Q is equal to dH at constant P. We also saw that delta Q is equal to dE at constant V. So there we did not have to introduce a new state function, but we introduced H. Later we saw that the natural variables for H, let's see if I remember, are SP and N. So I did remember correct. We saw this for H, and this did not lead us to free energies. This is where we had. In fact, we did not get to figure out what is SPN until much, that natural variables for H are SP and N until much later. How did we get to free energies? In order to get to free energies, we used our Clausius relation, Clausius inequality, which said that the spontaneous direction is one in which ds is more than delta Q by T, right? If this is happening, it is spontaneous. And this we transformed in different ways. We said this is equivalent to saying that dg of a system. So this is ds system, and this is delta Q heat given to the system, okay? This is equivalent to saying that ds system plus ds surrounding is more than zero, right? Because when you have system and surrounding together, then delta Q is per construction zero. System and surrounding today are system and surrounding together are an insulated system, are insulated. So this is problematic because we have to calculate the entropy change of the surroundings, and that's always going to be a mess. This one, we don't have entropy change of the surroundings, but we do have to think about path functions, which is heat given to the system. So we reformulated this in a way that it is only state function and it is only of the system by saying that dg system is less than zero at constant T and P, and dA system is less than zero at constant T and V, right? And for this, we showed that the functions that follow this property are G is equal to H minus Ts, and A is equal to E minus Ts. And then we started with this one. We started with this one. We said dE is equal to TdS minus PdV plus mu dN. And we were able to convert this. And actually, it's equivalent. You can go both ways. And I really recommend trying this backward way, this reverse way at home, where you do dG is equal to S dt minus V dP plus mu dN. So in class last time, we showed that this one implies this. We did not show this one. So this is good practice problem to show that starting from this, you can go back to dE is equal to TdS minus PdV plus mu dN. You should be able to show that. So this relation then showed us that the natural variables for G are T, P, and N. And we did similar things for H, we did similar things for A, and we got all sorts of other natural variables. So one more thing we did last time was to derive the Gibbs-Helmholtz equation. So this is all recap. And later in the semester, I will do like a 2-day recap where I will systematically, or even 3-day recap, and cover everything from very beginning to very end. So don't worry. Important things I will keep coming back to as we go further, and later we will do a full recap. So we also did Gibbs-Helmholtz, where we showed that partial delta G by T divided by partial T at constant P is equal to minus delta H by T square. So this is useful because if you have the enthalpy change, you can use it to calculate the free energy change. You can also go the other way, but normally this is what tends to be useful. So this hopefully gave you some perspective as to why this might be useful. Let's do more practical things with it. Today, we are going to use now dg is equal to vdp minus sdt for a constant composition system. Okay, we are not going to worry about the n part. To do something simple, we are going to answer this question. Why is it that for almost all materials, there might be an exception? So that's why I'm writing almost all materials. Maybe superfluid helium is an exception. I don't know. Something very funky might be an exception. Why is it that for almost all materials at constant P, as T increases, we get solid to liquid to gas? Okay, so what are we talking about? We are talking about all of this happening at same pressure, okay? For example, atmospheric pressure, but you keep increasing temperature and you keep increasing temperature. As you keep increasing temperature, you reach a certain temperature. At that value of the temperature, solid goes to liquid. Then you still keep increasing temperature. Nothing happens for a while, you stay liquid, then you reach a particular higher temperature, and that value of the temperature, liquid turns to gas. In other words, we are saying that solid to liquid to gas at a particular temperature and constant pressure. So I'm being careful with my wording deliberately. The pressure is never changed. There might be a bit of a lag in the video and so in the writing. So I'll write slowly. As the pressure increases, then at any given temperature, as the pressure is kept constant and you keep increasing temperature, constant pressure as temperature is increased, this is the preferred direction. So how do we prove this? Well, the way to prove this is the hint we already have here. We are thinking about constant pressure and we are talking about change at a particular value of the temperature, right? So what we really want to show that this is the direction for dg negative, okay? That's what we have to show. In other words, we would like to show that so let's call this as the T melting temperature, okay? That's the temperature at which solid changes to liquid. And let's call this as the T boiling temperature at which the liquid starts to boil into gas. So what we want to show is that i.e. T less than Tm, G solid is lower than G liquid than G gas. Actually, we don't care about these two. We just want to show that solid is lower than liquid and gas. That's what we want to show. Then at Tm less than T boiling, we want to show that G liquid is lowest. Okay, you exist as a liquid. And at T more than T boiling, we want to show that G gas is lowest. And the reason we are using G here because we are talking about a constant pressure process. If we were talking about a constant volume process, then we would be using the Helmholtz free energy to do the same thing, okay? So let's try to prove this. So we want to construct a plot for G versus temperature, and we want to draw curves for all three phases. One of these is going to be solid, one of these is going to be liquid, one of these is going to be gas, maybe the other way around. That's why I put a question mark. And we want to see how these curves looks like, okay? And we are starting at 0 Kelvin and going to very, very high temperature. Okay, so let's do that. At 0 Kelvin, what do we have? We have G is equal to H minus Ts, right? What is the value of G at 0 Kelvin? It's going to be H, right? Because there is no entropy. What is H? H is equal to E plus PV, right? So we know that volume of a gas is much more than volume of a liquid, which is much more than volume of a solid, empirically. Okay, so we know that the gas volume is much, 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 much bigger than liquid, than normally speaking for most materials. When the liquid becomes gas, it generally expands a lot. And liquid also tends to be higher volume than solid. Again, not true for everything. In fact, it's not true for ice. Things are funky from 0 degrees Celsius to 4 degrees Celsius for most material. Okay. So what does this mean? This means that at a constant pressure, PV gas is going to be much more than PV liquid is going to be much more than PV solid. So we know that this part of the G, which is PV, is going to be highest for gas, then liquid, then solid. We also need to think about E. Which one is going to have the highest E? What is E? E is the potential energy. Okay, it's the internal energy. So internal energy comes from two parts. Internal energy comes from kinetic energy plus potential energy. Okay, we are talking about 0 Kelvin. What is the kinetic energy at 0 Kelvin? You can type in chat.
0.
0 or say, yep. Why is it 0?
Because all molecular motion stops technically. I mean,
can you be more mathematical?
0 entropy at 0 Kelvin? I don't know. What?
No, don't use entropy. You're being smart. If you're confused, just say entropy, huh? Equipartition, right?
Oh, yeah, okay.
Equipartition says that per degree of freedom, this is half kT, right? But if T is 0, that is 0. But basically, even if you don't want to use math, it's okay to say that all motion ceases at 0 Kelvin, and kinetic energy is an attribute of motion. Since there is no motion, therefore there is no kinetic energy. Now we need to think about potential energy, okay? How is the potential energy going to look like? So for this, we need to invoke the picture of how does a general potential energy curve look for any material as, so this is the potential energy, and I want to think about for any two atoms, if the distance between them increases, let's think about the potential energy as a function of the distance between two atoms. How should the potential energy look like when R goes to 0?
Shoot to infinity.
Why?
Because at some point the atoms get really close to each other, so there's just high repulsive force between them.
Yeah, the electrons will start to beat each other, right? The electronic repulsion will dominate everything. So you start from infinity. As you increase R, it becomes lower and lower and lower. And then there is a strength at which they normally like to hang out together. This is when like a bond is formed, and then it increases. So a good form for this is A by R to the power 12 minus B by R to the power 6. Example. I'm not saying this is always true. This is an example. This is known as a Lennard-Jones potential. If you don't have to remember this for this class, we'll study it in StatMech in 687, but you can plot this curve and see that it looks something like this. So solids tend to hang over here. That is the energy of the solid. At 0 temperature, I'm just going to call it E solid because there is no kinetic energy. Liquid, on the other hand, is going to oscillate a bit more and it expands, right? That's the whole idea, that the volume is higher. So the liquid potential energy is going to lie somewhere over here if you look at this curve. So this is going to be E liquid. And the gas potential energy will be lying somewhere over here. Simply because liquid, solid, gas, interatomic separation increases. So therefore, E gas, and let me number the equations. Let's call this equation number 1, G is equal to E plus PV at 0 Kelvin. This is all at 0 Kelvin. And let's say, so we have just shown that E gas is more than E liquid is more than E solid. This call this equation number 2. So let's call this equation number 3. And this is equation number 2, that PV gas is more than PV liquid is more than PV solid. So if you think about G is equal to E plus PV, and you see that PV gas is more than PV liquid. So this part is highest for gas, the PV part. And we just showed that the E gas part is also the highest. E is also highest for gas. So together we can say that G gas is more than G liquid is more than G solid at 0 Kelvin, right? So this, hopefully I've given you some intuition using G that at 0 Kelvin, since there is no entropy, G is equal to H, there is no TS term, and G is highest for gas. So if we go back to this plot that we were trying to draw, let's draw it over here. What we have just shown is that if this is G and this is temperature, we have just shown that at 0 temperature, G gas is up here, G liquid is here, G solid is here. That's fine at 0 temperature, but we want to explain things at higher temperatures. We want to explain how will G change with temperature at constant pressure. How do we do that? Well, we use the fundamental equation for G. That tells us dG is equal to V dP minus S dt. Okay? Therefore, partial G by partial T at constant pressure is equal to minus S, right? Why is liquid at the minima in the potential curve? I did not draw liquid in the minima. This, oh yeah, yes, sorry, terrible. Must be my jet lag, really bad. That's bad typo, you're paying attention, good. This is solid. Very good job pointing it out. This is solid, that's the minimum. This is liquid. When you expand it a bit more, this is gas. Otherwise things would be screwed. Yeah, thank you very much. That was a terrible typo. So we have partial G by partial T at constant T is equal to minus S. Now this is the first time that we are actually going to use why is solid at the minima. That is where solid forms. Normally you tend to have face-centered cubic crystal. A solid at 0 Kelvin exists at the lowest possible energy configuration. A solid minimizes the potential energy per construction. Because if it was not here, if it was here, it would like to fall down over here. There is nothing stopping it. There is a crystal structure that bonds are formed and it likes to stay over there. So now let's think about it. This is the only time we are going to use Callan's fourth postulate, which we have not used otherwise, but which says that entropy goes to 0 at 0 Kelvin, and otherwise it's always positive. So that's entropy is more than 0. This is related to the third law of thermodynamics. We have set a value to the entropy. So if entropy is always 0, this means that G will decrease as T increases for solid, liquid, or gas. The question though is, so all of them here will, so the G gas will look something like this, okay? It will decrease. The liquid is also going to decrease. The solid is also going to decrease. Can we say, and it's not going to be necessarily a straight line. I just drew a straight line for the sake of simplicity. There is no guarantee that it is going to be a straight line. Most likely it is not going to be a straight line. So the straight line, straight only for illustration, because if the entropy depended on temperature, which it most likely does, then the line won't be straight. Okay, so which one is going to fall down sharpest? Anyone except Vedant? Vedant has been participating. We can type in chat also.
What was the question again?
Which one will fall down sharpest? So here I drew the curve for gas and I said gas is going to fall down at a certain slope. So my question for you is liquid going to fall down like this, or is liquid going to fall down like this?
I think gas would be the steepest. I mean, that's just my guess.
Why?
I mean, just thinking from a temperature point, and
it's the entropy, right? So this slope, the steepness comes from entropy. Okay. Yeah. So gas has the highest entropy. Kinjal, good question, good point. But now my question for you is, so basically our intuition and any knowledge of statistical mechanics that you have leads you to think that S gas is more than S liquid is more than S solid. Entropy is higher. But we have to be careful. So this is when you study in PChem that entropy is the number of ways of arranging a system. And you think, okay, gas is very disordered. We haven't really thought of entropy that way, but we can think of it as relaxation of internal constraints, right? A solid has the highest number of internal constraints, like there is nice crystal that is formed. As you relax internal constraints, the liquid can be a bit disordered. It still tends to have some sort of local symmetry, but the atoms are not really restrained to be on a crystal lattice. So this is solid, this is liquid, and this is gas. Okay, gas, everything is free. And what did we learn in Callan's postulate when we started? That as internal constraints are relaxed, the entropy goes up, right? As internal constraints relax, entropy increases. So this is one way of explaining something which all of you jumped to, is that entropy, gas has the highest entropy. And I'm just saying that we can think of it in a non-StatMech version by just thinking about internal constraint. Gas is the most free to move around. If you become ideal gas, for example, it should have the highest entropy, right? You can just move around anywhere because there is absolutely no constraint at all. So this means that partial G by partial T at constant P will be most negative for gas. So gas is going to be something like this. Liquid is going to be something like this, slightly lower slope. And solid, let's see if I can get it right. This solid is going to be almost flat if you think about it. It's going to be something like this, okay? Let me draw this picture in the next page. I will redo this on next page. Read it on next page using more space. This was page number 4. Okay, so let me do this one on the same figure as last page. So we just said that gas is going to have the steepest entropy loss. So this is gas, and this is G versus temperature. Liquid is going to be something like this, and solid is going to be something like this. Okay, it's the weakest. So this is gas, and this is liquid. liquid, and this is solid. Okay, so what does this mean? Let's look at this curve carefully. Until this temperature, solid has the lowest free energy. Okay, so this is our melting temperature. Until this temperature, the material would like to exist as a solid. Between that temperature, between Tm and this temperature, which is T boiling, liquid has the lowest free energy, right? The red one is the lowest. The red is lower than blue, is lower than green. Is there significance if the three phases meet? Oh, we will be doing a lot about triple point, Sophia. You're going to have a lot of fun with that. Yes, they can. And there is a lot of significance, not quite yet. We will get to that later. There are rules. The intersection points represent phase changes. Exactly, Jared, perfectly correct. So the intersection points represent our first example of what is known as a phase transition. Phase transition is arguably one of the most important topics in physics, in chemistry, in chemical physics, in biophysics, everywhere. You think about RNA, the hottest thing is liquid-liquid phase separation, and it's a type of phase transition. In society, people think about phase transitions to model behavioral change and everything. So phase transition is a very, very powerful concept. And this is our first example of a phase transition. And yes, three phases can exist at a particular point. Turns out not in a single component system. Actually, they can in a single component system. You cannot have more than 4 phases. So you can have a triple point of water. We are not seeing that over here. We will get to three things at the same time. As per this, at this particular temperature, at the melting temperature, you can have solid and liquid coexisting. And then when you further increase the temperature, liquid turns into gas. And now beyond this, it's gas everywhere. Okay? So we just use G and in an almost trivial construction to, and particularly we use this relation that dg partial G by partial T at constant P is equal to minus S to show for some arbitrary material, assuming straight lines, I mean, things will be complicated, things would be very complicated. In fact, we will see these G versus T type curves quite a lot when we go to phase diagrams, but this is your first example. Okay, any questions about this?
I had one. I guess it's kind of a question and kind of an observation, but since where the solid and the gas line overlap, it's like it's at a higher G value. Is that so if the G value is higher for a phase transition, does that mean it requires more energy for it to happen? Is that what that's saying?
No, what it means is that at constant pressure and temperature, as temperature is increased, so this wording is confusing. On one hand, I'm saying constant pressure and temperature, but then I'm saying as temperature is increased, as you keep doing this experiment at higher temperatures, you keep the pressure always the same. Stable phase is one with lower G. Okay, that's the whole point. So until this temperature, this has the lowest free energy. That's did not want to draw blue over there. This has the lowest free energy. The solid is the most stable. Beyond here, liquid is the most stable. Beyond here, gas is the most stable. Okay, is that clear or still confused?
No, that's clear.
Okay, good. Now, and here I have, if you look at the total free energy, it's almost as if there is a discontinuity over here, right? It changed arbitrarily. So there are people classify phase transitions as whether the G is discontinuous or not. If G is discontinuous, it's known as a first order phase transition. If G is continuous, but the first derivative of G is discontinuous, then it's known as a second order phase transition. This is known as Ehrenfest classification, the same Ehrenfest who you have seen in probably quantum mechanics. We are not going to get into classifications of phase transition, so I'm not writing it down here. Okay, so, and the thing to remember, so this is a useful example with this, and this assumes that it's a linear behavior, but it's quite true. But the more important thing that you really need to remember is that G drops with T at constant pressure. If I asked you, if I met you in the lobby or in the elevator, and I just went at you like, hey, tell me, why does G drop with T at constant pressure? Unless you remember the fundamental equation for G, which is dG is equal to V dP minus S dt, you won't be able to explain this to me, right? So it's really a direct consequence of this fundamental relation. It's really using this partial derivative and the fact that we assume that entropy is always positive. That's why G always drops. So this is one reason to why keep entropy restricted to 0 at 0 Kelvin, because you see it conforms to what we expect of change in, with change in material. So this was phase transition when temperature is increased at constant pressure. Now let's think about the other way around. Let's keep the...
Sorry, just a question. So our choice of G here is because we're like you can have phase transitions for any free energy, right? Or is it because only...
Yeah, because I set it up constant pressure and temperature. That's why.
No, but we did this, if I recall from the last class, because of at least for those molar quantities, because it was a natural variable of temperature.
Just an example, you can generalize it to constant volume and temperature. Then you will be looking at Helmholtz free energy.
Okay, fine.
And you can, so this is a good, again, a good practice problem. And maybe I will ask you it in homework or exam, is to think about volume, constant volume, particular temperature. Would you have a similar argument there? There you will have to think about dA less than 0, and you will have to think about what happens to A at 0 Kelvin, work through it and see if it conforms to your intuition. So you are keeping the volume constant and increasing the temperature. But we are going to look at one more which also uses G. And I also want to mention that partial molar quantities are normally, if it's not defined, it's normally for constant pressure and temperature. Sometimes you will see partial molar quantities defined at constant volume and temperature, in which case that's another story, but you have the machinery to deal with it now. Okay, so let's think about now what happens to stable phase when pressure is increased keeping temperature constant. So this one is a bit interesting. So again, let's draw our chart. This is G, this is P, and we need to think about how will the curves look like. So the first question is, last time we saw in G, the curves sloped downwards, right? Now the question is, I think my screen is hanging. Sorry, the screen was hanging, so. Okay. Everyone sees my screen? But it's still black. Do you? There is a terrible lag. Okay. Good thing this is the last class on Zoom. I will be back after this fully. Okay. People see my empty plot with G versus P?
Yep.
Okay, good. So we saw that in the plot with G versus P, it went down. It sloped downwards. What can we say for G versus P? Is it going to slope downwards or upwards?
Upwards.
Why, Michaela?
Because G is equal to H minus Ts and H is E plus PV and pressure is increasing.
Okay, that might be correct, but stay with me and tell me in using this relation. Upward is correct, but I want you to argue, Michaela, by using this relation.
let's see. In this case, I guess dp, if it's positive, would also.
So what is the value of partial g by partial p at constant t?
The volume and
can volume be negative?
No.
That will be a bad situation, right? If volume was negative. This is always positive. Therefore, G versus P curve increases as temperature increases, okay? Thanks, Michaela. So now, same thing which we used earlier, that V gas is going to be much more than V liquid, is going to be more than V solid. Okay, because gas very quickly has a much higher volume. I mean, hydrogen is the limit, but for almost anything. For this one, there is a problem, and maybe one of you can help me on Slack later. I tried to work through the ordering at zero pressure, but that's a bit tricky. I don't know how to do it. I don't know where will things exist at zero temperature, but it does not matter that much because the slope for gas is just so much higher than liquid and solid. And liquid itself is higher than solid that basically you will see something like this. Gas, sorry, that became completely vertical. I didn't want it like that. No. Gas is going to look something like this, almost vertical, okay? This is going to be gas. It's so much higher, the slope. Liquid is going to be something like this. And solid is going to be something like this. So I'm not saying that there is a small enough pressure in which the trend could be reversed, okay? It's possible that there is a small enough pressure at which the three things are different. But the point being that as soon as the pressure increases, gas is out of the question. It's not going to happen. That is the only conclusion we are drawing here. Whether we will have transitions from gas to liquid to from solid to liquid to gas at low pressure is something I'm not answering over here. You can go and think about it as to where should be the ordering be. But this is the main picture I wanted to give. Any questions about this?
I have a quick question. I'm kind of confused as to why for the G versus P diagram, there's all starts from one spot, whereas for the G versus T, there's multiple, like starting
because
positions.
Because I do a question mark here. If you zoom in, I don't know what is the ordering.
Okay.
This is, I am not sure about the ordering. And that's why I said, you can help me on Slack. I tried to think through it and I could not come up with a very good argument. I mean, let's try to think about it. What is G? G is equal to H minus Ts, right? Which is equal to E plus PV minus Ts. So we are thinking about zero pressure, right? So at P is equal to 0, we are thinking about E minus Ts. The reason why this one is difficult is because they are in competition with each other. You see my point?
Yeah.
So why was this so difficult for PT, which is my initial, is because E, and TS are competing. So you have to think very, very carefully. It might be an answer. Maybe I did not think through carefully. So, but the point being that I'm not going to care about it too much because this conclusion that gas is going to explode in free energy, that's robust because the slope is just so much higher. Okay. But you now have a toolkit, right? You can change things and you can think about what phase is going to stabilize. If you're thinking about something happening at constant volume, as the temperature is increasing, then you would think in terms of Helmholtz free energy. So you have the toolkit. Hopefully you're starting to see why all of this thermodynamic garbage might be actually very, very useful. Okay. So I don't want to really start Legendre transforms on Zoom. I want to be there and work with you on it. So we will do it on Tuesday, but I want to tell you so next time we will start Legendre transforms and I will tell you why the problem will happen. Why do we want to do Legendre transforms? And what we are going to do through Legendre transforms is to come to these free energies, G and A, and also the enthalpy H through a completely different route, okay? So you already have the tools that you need, but now we'll show it in a mathematically slightly more elegant manner as to why it happens. So So next time we will do Laurent transforms, and that is in class. We'll start Laurent transform. It'll take 1 or 2 classes. So the idea there is the two fundamental relations that we wrote down are S of NVE and E of NVS, right? And we showed that we could derive other fundamental relations by thinking about spontaneity. So in a sense, this is not needed. In the sense, you can be fine in thermodynamics without knowing Laurent transforms. But the reason why we need it and do it in this way is because if you think about these variables that are controlled here, that you know about, so you can write down the value of the function in terms of them, these are extensive variables, right? All of these. This is also extensive. This is also extensive. However, so in other words, in both energy and entropy representations, the mathematically independent variables are all extensive quantities. And independent and the intensive quantities were derived quantities. So if we could write down this function in terms where derived quantities. So if we could write this down in terms of extensive things, and then we calculate partial S, or let's look at the E1. If we calculate partial E but partial S at constant NV, we got temperature, right? Which is intensive. So it would be in a laboratory setup, or in any setup, it's very easy to measure the temperature, right? It's extremely hard to measure the entropy. It is quite hard to measure the energy itself. We have so many devices where we can measure the temperature. Same thing for pressure. Measuring pressure is easier than measuring the total volume or the total energy. You can just, the barometers are easier than going and doing an actual measurement on the whole room. You can easily measure the pressure, right? You're sitting in the room, you have an instrument that tells you the pressure. For the volume, you have to go and calculate everything. So we would like representations where at least one independent variable is an intensive quantity. Okay, so we want to have some function. Okay, let's call it self is probably an extensive function. Okay, it's extensive, and we want it to be extensive, comma, intensive, and maybe the third one is also intensive. Okay, or we want it to depend on something where it is function of extensive, extensive, intensive. Here is the question. Can we think of a situation where an extensive function depends on 3 things which are all intensive? Can this happen? It cannot, right? If all the variables that something depends on are intensive, and you double the quantity of the system, double the number of atoms in the system, it's not going to double. The function is not going to change. So for example, if you had something that looks like P plus T, and you double the quantity of the system, P plus T minus Q. I know I'm dimensionally incorrect over here, but imagine there are factors which are corresponding to the dimensionality. And things, you're not going to get an extensive function out of it. You can use extensive things and get an intensive function out of it, right? If you differentiate one extensive function with another extensive function, you will get an intensive function. If you divide extensive function by an extensive function, you will get an intensive function. So this is not possible. You cannot replace all three variables with intensive quantities. If you do that, you can do it, but this thing will no longer remain an extensive function. It will become an intensive function. It will have to become intensive. However, you can replace two of the values. So for example, N and V, you can replace with corresponding, N you can replace with mu, which is the chemical potential, and E you can replace with temperature, and both of these are intensive quantities. So next time we will think of this problem from a fairly formal but still intuitive setup, which is Legendre transforms, which is, it basically boils down to looking at a function y is equal to f of x and calculating f prime of x and trying to write down a function which is a function of f prime. So how to go from y as a function of f to finding out some other function that depends on the derivative. How do we do that? This is the subject of Legendre transforms. And you did this in the first homework, you read a paper. I know it was a bit confusing. We will go through it again, and then you can go back and read that paper. And at the end of this course, one of the things that I want all of you to be comfortable with is to see how changing free energies in thermodynamics is a Legendre transform, okay? We will do this next class in person in College Park. Any questions about this?
I have an unrelated question, but the idea that and like in StatMech or whatever you learn that entropy is a function of the number of odd arrangements or something of that sort. And then earlier in the class we talked about how it's higher for a gas compared to a liquid or solid because you have lower internal constraints. Is there some relation with concavity property and the like Boltzmann derivation for entropy as a number of arrangements? Like, I mean, completely.
No, I don't think you need concavity to do the. Yeah, you don't need concavity to derive the Boltzmann thing.
No, I know you don't, but I'm just saying that like you're talking about a system that's releasing internal. That's what that property tells you, right? Like the entropy of a system with no internal constraints will always be higher than that of one with constraints, and that's essentially equivalent in my head to saying that you're increasing the number of arrangements that the system could take.
Yeah. It is.
I'm just wondering if you can't derive, maybe you don't need it to derive, but I'm just like, if there is an analogy there.
No, you are absolutely correct. Hopefully it gives you intuition into why Boltzmann's relation followed, right?
Right, yeah, okay.
So that's the nice thing, isn't it? I don't know if I'll go as far as the concavity because concavity comes from the second derivative, right?
Right, okay.
So we are not talking about the concavity quite yet, right? So in order to write down S is equal to K log W, it also does not tell you about ln. I mean, we will do this in StatMech, and which I am also teaching. So it's great. You can, and most likely most of you will be taking it. So you can just ask me this like in the second day of StatMech. Right. But S is equal to K log W has log because it is extensive. It allows entropy to be extensive. And why it should depend on W in a monotonic manner, you can already see, yeah, this is our first hint. However, S is equal to K log W has nothing about concavity. Okay. That is a bit harder. We will think about it next time. So I actually, this is the first year that someone is teaching 684 and 687 in the same year, which I think is a very good thing because courses are connected. Normally it used to be John Weeks teaches 684, I teach 687, and there was a bit of discontinuity. So I think it's a good thing. We will continue many of these discussions in 687. So you keep note. And I do want someone to think about, where is Aiden? Aiden, are you still there?
Yes.
You asked me this question, so I want you to go and resolve this for me. Will you do that?
Actually, I do have another thing kind of related to this. So I was thinking, and I remembered that you could have phase diagrams that change based off pressure. So wouldn't that mean that the fact that there's a phase transition, that the gas starting point would have to be at the bottom and then to go liquid and solid at the top?
I don't think I quite understand your question. What do you mean?
So because I was looking at like phase diagrams, and if you lower the pressure or increase the pressure, you could change the phase of a substance or material. So would that mean that because everything's going up and you want the G to be the minimum point, that the gas would have to be at the lowest point because it has the highest volume like
it's
the
possible.
highest slope.
It's possible. So we will look at phase diagrams, we'll look at water carefully and other things also, and we will look at it there. It's possible. So I'm not making any claims about that region.
Okay.
I'm just saying that for a high enough pressure, this will be the case. I'm not, yeah, of course, many things can happen over there, and we look at it. And one of the things we did not do today is to define what is a phase, right? So when we finish Legendre transforms, we will actually think about what is a phase before doing phase diagrams. I've been casual about just saying phase. What is a phase? I just threw it out there. So we will be careful about it. Right now, it's just state of matter, solid versus liquid versus gas, but later it has a very specific meaning. Okay, good. So see you all on Tuesday. And once again, I really apologize for the delay in the class. I mean, I gave a talk today and then there was a Zoom meeting with my department chair. And, I mean, I don't want to miss class, so I teach, but Zoom world is a bit funky. Okay, take care, everyone. See you on Tuesday.
Sorry, sir, just for this thing of the start point, 2 questions. Like one, can we use some Maxwell relation to, instead of using G and P, use some other parameter to?
Sure. That's why I said open. I want to see answers on Slack.
And the second thing is, like, for the liquid solid slope, is it, would they be a lot closer? Like, because you have I don't know if you're considering compressibility at some, with more and more, as you're adding more pressure to the system, you'll eventually reach a point where the molecules are so closely spaced that the slope won't change as much, right?
Yeah, well, that's quantum regime, right? If you start.
No, I'm not talking about like quantum effects also. Like generally, if I'm thinking about a system with molecules and I'm bringing them closer and closer together, the slope of how free they are or how easily they move around, the volume as well, which is what the
slope. You saw something like that, right? You saw something like that. You drew the plot for thermal expansion versus temperature.
Right. Okay. But we haven't talked about
thermal expansion versus pressure.
Yeah, that's fine. So like the inherent notion of compressibility, is it related to the Gibbs energy or?
Yeah. They are all connected.
Okay. All right.
Yeah. So yeah, Omar, both G is not just T and P. G is T, P, and N. That's what I said. If it was T, P, and mu, then G would become intensive. H is also S, P, and N. There are 2 extensive quantities in H. A is T, V, and N. There are 2 extensive quantities. So that's why A is extensive. Okay, good. So see you everyone on Tuesday. Bye-bye.